Delamere Forest, Cheshire, a remnant of a royal hunting forest, probably originally deciduous woodland dominated by oak. But today, a coniferous plantation with Scots pine dominant. And we're going to look at the way in which soils can vary, even within a comparatively small area of the forest. This profile, it is of course a well-developed podzol, has been cleared in a bankside near a path, and it clearly displays several characteristic layers or horizons. At the top, leaf litter, and then a dark, almost black horizon. Below this, a very pale grey layer, much broader than the first. Another dark horizon, possibly made up of a number of thinner layers, which eventually merges into the orange-yellow sands upon which the soil has been formed. If we are to examine this profile in detail, samples must be taken from each horizon, preferably from the centre, taking care that sufficient soil is taken for several tests to be carried out, and ensuring that each bag is clearly numbered for identification in the laboratory. Any study must begin in the field, however. On the surface there is a layer of leaf litter, in this case pine needles and bracken. The dark horizon below contains this material in various stages of decomposition. This is the humus horizon, and the amount of organic material in this and other horizons can be measured in the laboratory. All the samples are allowed to air dry for about 2 days, by which time they're dry enough to be sieved. Each sample is then lightly ground to break up any particles which have aggregated. It's then sieved through a 2 mm sieve. This isolates the fine fraction, which will be used for further analysis. Each sample is then divided into representative subsamples using a riffle box. Each time the soil is poured into the riffle box, it's automatically divided into 2 equal portions. To establish the organic content, a weighed sample of soil is placed in an oven, which has been preheated at least to 750 degrees C. At this temperature, the organic material in the soil will ignite, producing a weight loss which is proportional to the organic content of the sample. After an hour, it is taken out and allowed to cool in a desiccator. This keeps it dry. And then the sample, its organic content now reduced to ash, is re-weighed so that loss of weight can be established. The pattern of weight loss in the profile is interesting. As expected, the percentage weight loss is very high in the litter and the surface horizon, but there is a second zone of concentration at a depth of about 30 centimeters. This is reflected in the dark appearance of these horizons. Both are dark brown or black. The upper layer contains plant remains, and the humus is comparatively coarse. Whereas in the lower horizon, the material is more amorphous. Indeed, it is even oily in texture. On the surface, the litter, which you can see contains many pine needles and pine cones, decomposes at a slow rate. One reason for this is the nature of the litter itself. Pine needles are very waxy, and this slows down the rate at which they decompose. A second factor which can slow down the formation of humus is the acidity produced by the decomposition of these waxy needles. Soil acidity is a reflection of the amount of hydrogen available to enter into reactions in the soil, and it can be measured by calculating the concentration of hydrogen. Some of this hydrogen is freely available in the form of hydrogen ions. The pH is the concentration of hydrogen ions in the soil. A larger proportion of the hydrogen is already bound to other molecules, but even this can ionize and enter into reactions. This bonded hydrogen, together with the hydrogen ions, make up the total acidity of the soil. Acidity is important because it controls the reactions which take place within the soil. Reactions which not only break down organic material and minerals in the upper layers here, but also allow them to be washed down through the profile and to be redeposited at a lower level here. This is known as leaching. The most widely used measure is that of pH, the measurement of free hydrogen ions in the soil. For this, a pH meter is used. This has two electrodes. The test electrode here, which is sensitive to hydrogen ions, and a standard electrode here. When immersed, the potential difference between the electrodes depends on the concentration of hydrogen ions in the liquid, and the measurement of this difference allows the concentration of hydrogen ions to be calculated. First, the meter is standardized using a solution of known pH. In this case, the reading should be 7, the point of neutrality on the pH scale, and the display is adjusted accordingly. A soil sample is mixed with water. A reading is taken. 3.6. This is a low pH, indicating that the concentration of hydrogen ions is high, and suggesting that soil acidity is also high. This is confirmed for the profile as a whole. Figures are generally low, but particularly so in the horizons with a high organic content. How does this compare with the picture for total acidity? To measure this, the samples must be carefully prepared. An extracting agent is added to the soil and water mixture. This will release all the available hydrogen into solution so that it can be measured by titration. The samples are agitated for at least 1 hour. Each extract is then filtered and measured. The subsequent analysis will be performed on this filtrate. Total acidity can be measured by titration against a standard alkali. We're using, in this case, sodium hydroxide solution. The amount of alkali used to neutralize the acids in the soil gives the total acidity. If total acidity is plotted for each horizon, it is clear that there is, in this case, a strong relationship between total acidity and soil pH. You will see that high total acidity figures correspond to low pH values, and both are highest in the horizons where organic content is high. That is, in the surface layers and in a zone of redeposition below. But if organic material is being leached through the soil by the rainfall, what about the minerals in the profile? Simply by continuing the titrations we've just seen, the concentration of one mineral, aluminium, can be measured. If sodium fluoride is added to the neutralized solution, it reacts with the available aluminium in the solution and releases sodium hydroxide. This is, of course, an alkali, and it can be neutralized by titrating against a standardized acid, in this case, hydrochloric acid. From the volume of acid used, it's now possible to calculate the amount of available aluminium in the solution. Once again, the results for the profile as a whole are interesting. The effects of leaching are again apparent, and redeposition is obviously taking place at depth. It is significant, however, that the aluminium is not redeposited in the same zone as the organic material. The main concentration is slightly lower down the profile, indicating that the zone of redeposition is much wider than seemed at first sight. This is the pattern for aluminium. Are other important minerals distributed in a similar way? To measure the concentration of some other minerals in the soil, a flame photometer can be used. A solution is drawn into the instrument along a thin tube. It sprays into a flame. Metals in the solution cause the flame to change color. Colored light is directed through the flame, and the intensity of the emerging light is measured by a photoelectric cell, and a reading is given on the galvanometer. This reading can be used to determine the concentration of certain minerals in solution. Let's look at the distribution of some of these important minerals. Potassium tends to be concentrated in the upper part of the profile and in the zone of redeposition. But calcium is mainly found in the humus horizon, suggesting that it is being taken up by roots and is returned to the surface in the leaf litter. Both minerals are poorly represented in the pale horizon, below the humus layer, suggesting that the effects of leaching are greatest here. The dominant process at work in this area is leaching, and the movement of both organic material and minerals down the profile and their redeposition has produced the horizons which are so characteristic of podzolz. And the texture of the original sand has also clearly been changed. In places, the soil is still obviously very coarse. Here, for example, in the leached horizon. In other places, the material is fine and the texture is almost oily, as we see here in the zone of redeposition. The scale of these differences is reflected in the particle size distribution, which can be measured using simple equipment. First, the organic material must be removed by adding hydrogen peroxide. This digests the organic material in the soil, and to speed up the process, we place it on a water bath. A dispersing agent is added, and the solution is agitated. The soil is then dispersed in water, and the density of the mixture can be measured using a hydrometer. This looks like a standard hydrometer, with a glass bulb, weighted at the end with lead shot. But the stem is specially calibrated to show the percentage of material in suspension. It's shaken, and 2 readings will be taken. The first after about 5 minutes, when the coarse material, or sand, has settled out. A second reading is taken 2 hours later, when the silt has settled. From these 2 readings, it's possible to calculate the percentage of sand, silt, and clay in the sample. It is the distribution of fine material in the profile which is most interesting. This confirms that leaching is the dominant process at work. Since the organic material in the samples was digested before analysis, there are no figures for the humus horizons. But in the horizon below, there is little fine material, less in fact than in the parent material itself. And this suggests that it has been washed out of this horizon, and redeposition of fine material has obviously taken place below this. The soils which have developed here reflect the parent material, in this case, sand. The vegetation cover, which is here Scots pine with bracken and grass, and the climate, and in particular the rainfall, which gives a dominant downward movement of water through the profile, produce both the leaching and redeposition of organic material and minerals. This is the situation under Scots pine. What happens to the soils of the forest edge, where the vegetation changes dramatically, first to deciduous trees, and then to arable farmland? Here, for example, the vegetation is very different. It is obviously broad-leafed and deciduous, predominantly sycamore in fact. There is less litter, suggesting that it has decomposed more rapidly. And this is confirmed by the profile itself. The humus layer and leached horizon are much less distinct. The root network is obviously denser and deeper, and there is more worm activity. This indicates that while leaching is still taking place, it is less important and there is no clear zone of redeposition. This, in turn, suggests that this soil is less acid. Let's test this by measuring the pH. A sample of soil is placed in a test tube containing barium sulfate, which will clear the suspended solids. Some distilled water is added. The test tube is then shaken. Next, an indicator is added, which changes color, and this color can then be compared with a standard color chart. In the previous profile, the pH was about 4. The comparable figure here is 5. Less than 50 meters away, the land use changes yet again. This is a field laid down to spring barley. If we dig a pit in this field, the profile reflects the change, and in particular the effect of ploughing. The upper horizons have been destroyed, and there are now only 2 distinct layers, separated by a plough line at a depth of about 25 centimeters. Roots and wormholes are plentiful in this upper layer. And a pH test gives much higher values, suggesting that soil acidity has been reduced by application of fertilizer and lime. These changes can be related to changes in vegetation, but here on the slope leading down to a small pond, only a few meters from the first profile, the vegetation is still predominantly Scots pine. And if we look at the soils which have developed on this slope, it isn't a Catina. The differences are striking. At the top of the slope, the profile bears a strong resemblance to the first profile. The humus horizon is well defined, a thick leached horizon, and a zone of redeposition. A few meters down the slope, and the profile is very different. A confused mixture of organic layers and light-colored sands, scattered throughout the profile. At the bottom of the slope, near the pond, there's a thick layer of organic material. It's fibrous and not like the humus seen in the other profiles. It is, in fact, peat. And below this is a layer of sand. Both layers are waterlogged. Why do these changes occur? The same sands underlie the 3 profiles. The vegetation cover is similar, if not identical. And there can obviously be very little difference in the climate. Why then are the soils so different? The changes we have seen can be understood not in terms of soil type, but in terms of the processes at work. Processes which have caused the original podzol to be modified in so many different ways.